Hi guys, this is Nikki Brady. I'm going to be doing a video presentation about a research paper that I did a review on that talks about the impact of supernovas on the Earth's atmosphere and more or less kind of just tracks when they happen and why they happen and what kind of instances they happen. This paper was written by Mads Sorensen, Henrik Svensmark, and Uffe Greg Goranson, and it is titled The Near-Earth Supernova Activity During the Past 35 Million Years, and so they have a lot of data and research that they've done about this topic to show the time scale of when the most supernova activity was seen in open clusters and how close it was in parsecs and how this could affect us to present day. So 35 million years of supernova activity. The goal of this paper was to measure the near-Earth supernova activity within open clusters, which are gravitationally bound, long-lived stellar groups, which have a mean life of about a few hundred million years from the start of the formation to the end of the core collapse. And this is seen to be to about 35 million years that they've done their data, to which the most activity was and how it may have corresponded to the activity of the Earth's climate and geology change. And so I'll be talking about the importance of this discovery, the calculations and methods, the result, and why or why not we should believe these results that they have taken, and what does this mean for what we know about the universe today. I chose to do this paper primarily because I'm a geology major, and I thought that this was really interesting to see how these events have affected the geological component of Earth that we know it as today. And so these supernova activities that are near Earth within 100 parsecs has actually affected the geology and the climate change of Earth. And so this has been recorded to possibly have affected the life on Earth in a ice age and more of a overall Earth extinction that has left traces of different elements on the Earth. And so these supernovas are primarily caused by single and binary star systems, which can also kind of show us the importance of these different supernova progenitors. And this also is important because this can allow us to predict future events that can happen on Earth by scaling out the time that these typically occur, which is every 2 to 4 million years. What drew me to this paper in particular was that the mass loss from the supernovas were actually deposited onto the Earth. Gamma rays and mass loss penetrated the Earth's atmosphere and affected the composition. What is interesting is that iron and beryllium were found in large traces deep in the oceanic crust and were also found along the continental crust, which is interesting because the Earth's atmosphere is primarily made up of nitrogen, oxygen, argon, and carbon dioxide. Assuming that these deposits were carbon dated, which is common in geological studies to find specific time periods, we can use this as a concrete timestamp for analyzing when these supernovas had occurred near the Earth in a particular parsec distance. Gamma rays in particular are especially harmful during the supernova event by inducing a chemical reaction in the upper atmosphere that converts molecular nitrogen into nitrogen oxides, which depletes the ozone layer. This is troubling because it exposes the surface of the Earth to harmful solar and cosmetic radiation. Near-Earth supernovas also cause the increase of TeV and PeV energy-range cosmic rays, the increase of tropospheric ionization, and muon radiation on living organisms on Earth. All of these effects depend on the field orientation of the supernova, and the chemical levels return to normal within 10,000 years. When analyzing a specific open cluster, the past position relative to the Sun is important to know distance and how exactly the stellar content had evolved. Most of the calculations started with the base distance in the solar neighborhood from the Earth at around 1 kiloparsec to allow a time jump of 35 million years. Several graphs have been made to demonstrate the data calculated during the study, like a spatial temporal 2D probability density map and a time series of supernova activity, which will be shown later in this presentation. To start the calculations, modeling the galaxy with respect to right-handed Cartesian frame of reference is important to decrease the uncertainty. The scientists traced the trajectories of the open clusters back in time with the right-handed Cartesian frame of reference, and then solved the equations of motion to compute the conserved angular momentum. The age and current mass of the open clusters allowed for a semi-analytic model to then find the birth mass of the open clusters. Once the birth mass was found, this would allow for the calculation of supernova progenitors within the open clusters. When the number of progenitors were found, the temporal distribution of near-Earth supernovas from each open cluster will be calculated by applying a modified version of the binary stellar evolution code. When finding the temporal distribution, this led to Monte Carlo simulations to be ran by combining the trajectories of open clusters with evolving single and binary stellar populations, leading to the following figure on the next slide. Tests were then ran on each open cluster calculated to find the distance of supernovas to the Earth. Looking at the distribution of stars initially in each open cluster allowed for the scientists to observe how the Sun passed by these open clusters and absorbed mass from the formations. So during these calculations, this allowed for results to be calculated. This is a spatial and temporal probability density distribution of supernova events from open clusters spanning over 35 million years ago to now. It is seen that no supernova activity is observed within 100 parsecs of the Sun during the 5 million years mark, which contradicts the knowledge that iron ISO 60 anomalies were found during this time on the Moon and Earth. Seeing that these deposits were geologically carbon dated, I believe that this is a flaw in the data that was caused this data gap. The study states that this can be a cause of open cluster association that produced close supernova activity 2.8 to 2.2 million years ago that was not found within the used data. This can be explained by the lack of data on this specific time period on the data chart, or that this source was from a high-velocity runaway star, or binary evolution, which is unlikely. The first table in the 395 open clusters used to calculate the distance of the supernovas in respect to the Earth. The columns have the name, age, mass, position, distance from the Sun, proper motion, and radial velocity. These measurements were used to calculate the heliocentric position and local standard of rest velocities shown in Table 2. This allowed for the reconstruction of supernova events to occur. Here we assume all errors in Table 1 and 2 are Gaussian. This figure shows the distance to the Sun of the open clusters that have ages less than 40 million years, shown in red lines, and the open clusters with ages greater than 40 million years, shown in the gray dashed lines. This spans over the past 35 million years through the data found on the last slide. Binary interactions extended the time of supernova events to 200 to 250 million years. Single binary stars caused the supernova events to last less than or equal to 40 million years. With supernova events that last less than 40 million years, end because of core collapse. Events that are from 40 to 200 million years are affected by binary evolution, causing merging or mass transfer. The data shows that 18 to 12 million years ago, 5 open clusters came within 100 parsecs of the Sun, potentially housing supernova progenitors. 10 to 5 million years ago, a grouping of open clusters is seen 200 to 300 parsecs from the Sun, moving away from the Sun. 3 to 2 million years ago, a single open cluster is at a distance of 100 parsecs, able to house supernova progenitors. Finally, no open clusters is seen within the kill radius of supernova explosions, around 10 parsecs. This table shows the overall results from the Monte Carlo simulation to find the distance of supernovas from the Sun. Columns 1 to 7 show the name of the open cluster, the age, its minimum distance, time before present of minimum distance, age of open cluster at a minimum distance, the cluster's birth mass, and the median number of supernovas produced by the open cluster. columns 8 to 14 show the probability that a supernova event occurred within the open cluster, while the open cluster was a distance to the Sun of 1 kiloparsec, 0.8 kiloparsecs, 0.6 kiloparsec, 0.4 kiloparsec, and 0.2 kiloparsecs, and 0.1 kiloparsec. This graph shows the delay time function, or a supernova response function, following a 106 mass of the Sun starburst. This shows the strength of the varying strengths of the different progenitors typed supernovas, seeing that the single star systems are the weakest and the combined star systems are the most destructive. The volume of supernova rate is shown with the red curve, and it's showing the open cluster mass decomposed into the supernova events from the primary stars, which are shown in blue, and the secondary stars, which are shown in green, and the single stars, which are shown in cyan. So this shows also the strength of the different star systems. Is this believable? During this class, we have been told various times to take every article we read with a grain of salt, as scientists like to assume more than what is found sometimes. Seeing that we have deposits on Earth that give us the ability to carbon date the evidence of supernova activity, I can believe that the data found is believable for the concrete evidence that we have. Seeing that some of the data was not aligning with the carbon dating of the iron, carbon, and beryllium isotopes, I believe some data is lacking from this study. It is believed that near-Earth supernova events aided the creation of our solar system from the mass loss of the open clusters through supernovas, especially with the iron-60 isotopes. This allows for the past supernovas to be detectable on Earth in the form of metal isotopes found in rock strata. The paper stated that a lot of uncertainties came from a list of observations. This comes from the lack of data found for the time period of 2.2 to 2.8 million years ago, aligning with the findings of the element deposits, the oversimplifications of mass estimates of open clusters, assumptions of supernova positions by the center of open clusters, distribution of primary, secondary, and single star supernovas, runaway star effects, and the decay of supernova rates. Seeing that a lot of data was assumed rather than precisely calculated, which isn't unexpected considering the technology we have is limited for what is trying to be analyzed, I am wary to take this data as fact. I do believe that primary and secondary star evolutions is more significant towards supernovas rather than single binary star evolutions. I do believe that the data gave us a rough estimate on tracking the supernova activity that has occurred near us. This can give a good foundation for finding the exact effects that these systems have had on the Earth's atmosphere and lead to more precise data. Also, I photoshopped this image specifically for this slide. What does this mean for us? I believe this paper can contribute to understanding the history of our Earth a little more than we already know in terms of what has happened in a more atmospheric scale. I absolutely love studying the history of the Earth and would love to know more about what has happened in terms of Ice Age, total Earth extinction, and why these occurred. Seeing how there are so many theories in geology about what has happened to make the mass extinctions, more knowledge about supernovas can certainly clear up many theories. For instance, many geologists believe that the dinosaurs were wiped out by a meteor strike, which is a firm assumption considering the traces of meteors that had been dated for these timescales. However, something very exciting I discovered when reading through this paper was that the dating of the iron-60 isotope was around 2.2 to 2.8 million years ago, which was also the start of a new geological period, shown in the chart that I provided. The Quaternary period was coined the Great Oxygenated Period, leading to the rise of living organisms, especially humans. I believe that the supernova activity was found during this time period, assisted to the time period change, and that we will continue to see a correlation of geological events to near supernova activity. And these are my sources that I used for this presentation. Thanks, and have a great holiday!